Alright, another draft physics video presentation. Get rid of that. Anyway, so, yeah, there's not much going on as usual. There's just no way to generate any kind of conversation. So again, I'm offering $1,500 to a channel with 100,000 subscribers or more for an hour of their time to defend conventional physics and such, against my questions, my interrogation. And frankly, I would just, if somebody wants to have some sort of, there should be a capacity to have video exchanges on this medium, and it's just like nobody's capable of it, which is kind of bizarre in any kind of rational way. It seems to be a working mechanism of having an argument is a person makes their contentions and then somebody counter argues in some sort of relevant way, hopefully. And you do that back and forth and kind of get to the core of the disagreement and, where it lies. And I think clearly here it just lies in the sense that people have faith and, they really don't need evidence to support their understanding. They just believe and hope, and wish, and do a lot of things that aren't very scientific. I make that argument. They aren't very argumental. That's the whole point. I keep analogizing this to like a courtroom, like an ideal courtroom, like not the ones we have now, but the ideal way that, you just have advocates who present arguments and present the evidence and show it to a jury and explain it and say, this is why you should understand it this way, is because, look, the facts all add up to it. And there's a lot of facts. And if seen in that context, the trial of conventional physics would be a mistrial, because the jury would say, you don't have any evidence. You're just arguing that, gremlins and pixies. But anyway, you got to do better than that, frankly. Again, it just seems like with, obviously this is an obscure channel, blah, blah, blah. There's no networking possible for the dissidents. In a sense, because they're not going to play all the networking games and all the buddy bullshit and popularity requires and all that nonsense. So by definition, they're outsiders and they're going to be kept outside in some respects, until they're relevant outsiders, and becoming relevant requires a plane to crash on your house or you to be a lunatic. There's no other way to become relevant, apparently. So this is a daunting task and continues to be one. So all I can do is, play other people's content and show it to be flawed and continue to demonstrate that there's no good reason to believe the scientists. They frankly are showing that they don't have much integrity. They don't really care about the truth. They don't care about the rules of the game they're supposed to be playing, the evidence rules, and all of that mush. Instead, they're just singing songs. So, in that vein, I got comments by a 13-year-old, an arrogant 13-year-old. Like, we need this in the world. Like, somebody has to explain to this little putz that, you're 13 fucking years old. Kind of understand your place in the world. You haven't had much time to really make evaluations about anything. And I'm sure whoever raised you, has, shoved a bunch of nonsense into your little poor brain that you're going to find out eventually is nonsense, And so one rule you ought to figure out is that you don't type 4 different comments that are less than a sentence, frankly, long on a video. It's just kind of rude. You watch a video and then if you have something relevant to say, you say it. Okay, something that means something, not just mush and gibberish. This is what you're of the modern generation, and what you've already picked up these rotten and bad habits. This isn't how you use the internet. Okay, it's not for this kind of just junk. Okay, oh my god. Yeah, that's very useful. Wow, just insanely useful. Mush. I could type that on any video on YouTube. What's the point of it? Oh, you think it's incredible. Oh, the 13-year-old thinks I'm incredible. Yeah, amazing. You are judging theoretical physics too quickly. No, you are, idiot. You're 13 years old. All right, I'm judging it after decades of letting it roll around in my head and try to make any sense out of it. Okay, this whole idea of a bending 3 dimensions. Go ahead and try to make something 3-dimensional, then bend it for me. Okay, show me how you bend 3 dimensions. you you don't understand any of the theoretical physics. It's way too convoluted. You just can't do it in 13 years. I'm sorry. It's not possible. So you can't be an expert. So how the hell are you judging? He calls himself the astronomer, like, you're going a little, aren't you just racing a little too fast? Just slow down a little bit and say, well, maybe I ought to figure out what I'm talking about before I talk about it. So anyway, a silly thing to say. Judging it too quickly. I've spent 10 years working on this channel, developing my own theory, which in substance is what the channel is about, a rational theory of the universe's function, an evolution theory to contrast against the made-up, magical, entangled, woo-wee bullshit of the theoretical physicists. They theoretically think one electron could be doing everything in the universe at once because it's a time traveler. Do you believe that crap? That's the kind of thing Feynman wasted his time on. Ugh. So another piece of crap as a comment. All right. Is it a crime to try to solve the mysteries of the universe? So again, I'm all for it. From the time before I was 13 years old, I could figure out that this wooey description of a photon, is this wavy thing, sounded way too complicated. Like, how does a photon know it's supposed to be doing all that crap? Where's it figure that out? How does it curve even? We know that evolution takes a while to make snakes and lizards and do these different things and create, capitalize on different kinds of mechanical functions that it can give creatures, and that it takes a lot of trial and error to find these things that work. And how does a photon figure out to have all of that sophisticated behavior? You don't answer my question, of course, because you're not even going to watch any of these videos. You just do your little tripey comments and then run like a little sissy. That's all you're going to do. But anyway, so I'm all for solving the crime. The point is that we're at trial now, okay, and the evidence is on the table. And the argument is that the 2-slit is garbage evidence, okay? They've been lying to you, okay? They're telling you a story about what kind of detector experiments they did, in this story and that story. And they're all just stories, and their own mathematics that they say is perfect doesn't even work. And the wave centers are in the wrong places, and all of that crap that I've already illustrated. So they're sitting there looking at the evidence on the table. They're not honestly describing it. I'm showing you as a juror, I'm saying, look, okay, they can't even accurately describe a 2-slit experiment. And you trust them when it comes to things like gravitational waves? I mean, it's your bad here. Sorry. But you're the one in the talking shite position. Junior. Alright, garbage. Transistor TVs and the internet all came from theoretical physics. See, they've taught you this bullshit propaganda, and that's all it is. I actually was working with these things as they were developed. And they were developed by trial and error. The first laser diodes, okay, they cost $35 and lasted 6 hours. Alright? It took a long time to get it right, and had nothing to do with any theoretical physics. It had to do with, hey, we have LEDs, let's see if we can make them stronger and more powerful. Let's see if we can make them brighter. It took them 25 years to go from red LEDs to blue LEDs. You think it was 25 years of theory? No, it wasn't 25 years analyzing the theory. It was 25 years of changing the chemistry of the compounds to see if they could make something else happen. It was trial and error. So this is all just hype that this had something to do with a theory. It didn't have anything to do with a theory. Einstein essentially discovered, the photoelectric effect in the sense of he built the first photodiode, in a sense, you could argue, converting light into electricity. But it took them another 30 or 40 years to figure out how to make it work. So it wasn't because they didn't have a theory. Theory had nothing to do with it. It has to do with, again, mechanical perspiration. It has to do with the Edison theory that invention is 99% perspiration and 1% inspiration. Idiot. Asshole. Little punk. So really, take your tripe elsewhere. Fuck. Arrogant 13-year-olds. It's just too disgusting. Alright, so in the end of the rest of this is all just crap, frankly. I don't mean anything negative. Some of this stuff is relevant, I suppose, to somebody who cares, but I'm looking for arguments. I'm not looking for followers. I'm not looking for believers. I'm not looking for restatements of what I already just said. Let's see what this is. A magnet under iron filings will show the lines of field. Well, that's just too brilliant. The context of all the videos I have made and explaining exactly how the position of every one of those little magnets is decided by straight line forces from the north end and the south end of the magnet. You can draw the straight lines. Alright, the curved line is made out of straight lines. That's the facts. That's the mathematics. That's what Maxwell showed. So again, there's no curved lines in Maxwell. There's a bunch of straight line vectors. Look it up. Just more rubbish, Oh, it's brilliant counter argument. Iron filings make a pattern. God damn. It's very hard to suffer this. Alright, so we'll just do some of this Wolfram guy. So he's semi-famous, but he doesn't have too many subscribers here on YouTube. Only 44,000. Has some sort of unification theory that's a bunch of computer gibberish, frankly. It's kind of like a chaos theory, that somewhere in all the numbers you can pull patterns out. And certainly that's true, but I don't think that's you're not going to get to the core functions that way. The core function is charge and gravity. Gravity, the absorption of momentum. And that's all there is, really. There's the fact that when little elemental bits, electrons and protons, move, they absorb energy out of the universe to do it. Force has to get used up, essentially. It has to be slowed down, moving matter. And in doing that creates gravity. And then the fact is that the charged elements are different than each other, and there's a subtle difference in the force, and those two inversely play with each other, and that makes it possible for electrons to act completely opposite of protons in the field of force. That is all there is force bits of force. And they could be inside of things and they could be outside of things. And the force bits are either moving electrons and protons or they're flying freely through the space. And that's the only two forms they have. And the matter only has the form of being pushed by some stuff or not being pushed by stuff. And that's the only two forms it has. Two states. So anyway, we'll jump ahead in here. He's doing a description of the history, and the history is kind of, frankly, who cares? I mean, it's it might be important to somebody, but it's not terribly important to me when they discovered something. The point is you discover things, and you list the things you discovered, and that would be the thing they should do, is write down a list of the things they've kind of know to be sure for proof. that we know it for a fact. And they have a bunch of things on that list. Newton was right about a lot of stuff, but the fact is when he talked about the laws of motion, he wasn't talking about electrons and protons. He was talking about bigger things. Things that are made out of atoms, the rules of atoms, not the rules of electrons and protons. So this idea that once you put something in motion, it keeps moving, it's not the rule for electrons and protons.
About what?
All right, turn it up a little bit. I got it sped up, but yeah, you'll live with it.
What the role, the notion of whether a vacuum really had nothing there. So what?
Let's see. I think I have it sped up. Yeah.
One of the important ones of those was people knew about sound, and they knew that sound was compression waves in the air. And
yes, compression waves doing this, when a compression wave would be this, right? So they don't even really describe what these waves are. And again, waves are waves of what? Waves are medium-based. There's no other way to think about them rationally, in my opinion. Unless you start thinking about waves of soldiers, and then you understand that, oh yeah, they're just individual soldiers, and I can line them up like waves. I can produce them in groups, and I can make it quite obvious. So I've sort of made the point that all you have to really understand about what's waving in, say, an antenna is if there is this idea that there is force all the time, like light, and it's shining around me, right? Now if I move forward towards you really fast, okay, all of the photons and all of the space that's in front of me are going to have an interaction with me sooner than they would have. So in the same amount of time, a little millisecond of time, all of those photons are going to reflect to you. So you're going to get a whole bunch of them, a whole bunch of soldiers. Now if I move away from you fast, very fast, 3/4 of the speed of light or some kind of silly number, very fast, then none of these photons, all of these photons in space moving towards me, none of them are going to hit me. None of them are going to reflect. None of them are going to go back to you. So I'm going to become invisible. So that's creating your wave in electrodynamics. All the, the mere fact that things are going these two ways. They go forward, they go back, they go forward, they go back. You can understand that when they're going forward, they're compressing. They're putting a whole bunch of stuff. Now, all the stuff hitting them is now going to reflect. And then when they're going back, none of this stuff is going to reflect, and they're going to be essentially invisible. There's going to be nothing in space reflecting back. So stuff went in, and nothing's coming back out, right? So that's your dead space. That's your frequency. That's your wavelength. That's what's causing it, is the movement of electrons. And again, it's more than one. You can't make a photon out of one electron. It would have zero polarization then. It would be impossible to trap it by using polarization films. So there's no light. We can't shine a kind of light. Like if I take a polarizing film this way and I turn another one going the opposite way, I can't shine any form of light that gets through both filters. I can't make a photon that can do that. So I obviously can't make a photon that doesn't have huge polarization. So I can't do it.
Also have sound in solids. It was compression waves in solids and things like that. And people like Helmholtz, I think 1860s-ish, had developed a pretty complete theory, mathematical theory of sound. That Rayleigh, I think, had a version of this. In fact,
so yeah, but the complete understanding would have to have something to do with the fact that sound has a speed, and they don't talk about that very much. The speed of the medium, the speed of the atoms. So the atom sizes has something to do with how fast you can transfer sound through a medium, what it's composed of, how much oxygen versus hydrogen versus nitrogen versus blah blah blah. I change what the mixture is, and I change how fast this vibration can pass through the medium. So the compression has to do with how the atoms are banging into each other, and in a specific way they bang in a way where all of the energy is conserved, and that is it moves through one direction and it doesn't lose any energy going the wrong way. So the idea is if you move something quickly enough, all right, it doesn't have the choice of moving up or down. It can only go that way. And that would sort of be relevant to the speed. And the whole argument I would make is that all sound has to be created by movement faster than the speed of sound. So this is something that physics has never really come to having a conversation about, but what's the nature of making sound? And the nature of making sound is speed. So the faster you move something, the more likely you are to create this efficient transfer of the energy through the atoms. And if you're below that minimum, then the stuff goes in all kinds of directions. So it's kind of like a pool ball analogy when you have the balls right next to each other actually touching each other versus having to roll into each other. You get a different outcome. How else to put it? So the energy doesn't transfer through very efficiently until you have compressed the atoms by moving very fast. And when you compress them and move very fast, then you can break them, so to speak, in a way that the energy transfers in one direction. So and there's probably lots of analogies for this speed argument. Bullets going through bodies. I make the bullet go slow, then it tears a whole bunch of stuff to pieces. Lots of friction, lots of stuff goes on. The faster the bullet goes, the more efficiently it tears through whatever it's in the medium it's tearing through. It's like poking a bucket of sand. I don't know if that one really works. You'd have to go very fast, really, to create a wave in sand. The speed of sand. To create a sound transfer through sand would require a really high velocity, you could argue. But the point is you have to break the sound barrier, essentially, in terms of your speed, to create the wave that moves efficiently, that you're going to have as sound. And it just has to do with how efficiently, how much you keep the momentum moving in one direction. And it can only move in that one direction when you go fast enough. And if you go too slow, you lose all of your energy with a bunch of motion in the wrong direction. I guess going into the earth is a good example. If you were plowing into the earth or something, if you push in slowly, then the earth can move sideways and can move in lots of ways to undo your pressure that you're applying. But if you apply the pressure with a certain speed, then you prevent the deformations in the wrong direction.
His book, Helmholtz and Rayleigh's books on sound, I certainly have copies of them, and I think they're pretty modern, actually. There's not a lot, so you can say more techniques, but they pretty much have nailed the way sound works and the mathematics of sound waves and so on.
So again, it's mathematics, but yeah, they got some of that down. But again, it's one of the critical parts to making one of these waves. Even though you can see it with a rope, you have to move the rope fast to get the wave to move through the rope. If you move the rope slow, there's no wave in the rope. The rope doesn't acknowledge that you're creating a wave. You have to move faster than the speed that the energy will transfer through the rope. The speed of the rope, you have to move the rope faster than that to get the wave to efficiently move through the rope.
But there was a question, come to a little bit more later, but there was a question for electromagnetic waves. We know that sound waves are compression and rarefaction waves in air, in a material. The question is, what are electromagnetic waves in?
So again, this idea is waves in. We know it's a medium. We know it's made out of stuff, little bits, and the little bits have to be connected to each other. There has to be a tension between them. Like the sand argument, the sand has very little adhesion between the little bits. So there's lots of ways that it can go in lots of directions, the energy, so you can lose it all. And the idea is the atoms are connected to each other, and all you're trying to do is reduce the amount of like I said, sideways direction. And like non-compressible fluid like water sort of explains it, like, yes, if you're going to push it in this way, it has to go up and down. It has to expand somewhere because it's not compressible. The atoms can't be compressed. but they have to be tied to each other. There has to be an adhesion between them, either caused by an external pressure that's forcing them into a container, or because they have an adhesion like water molecules, because they're sticking to each other.
And so this notion developed of this thing called the ether, the so-called, in a very Victorian sounding name, luminiferous ether, the light carrying ether. That was the idea was that there was this unseen thing that was the analog of what air was to sound, the luminiferous ether was to electromagnetic.
Right. They still believe in it. They just don't call it that. So again, there's still this argument that these fields, electric fields, is the electric ether and the magnetic ether. These are still exactly the same concept. They haven't changed it at all. They just give it a different name. But the idea is still the same. It's as if the fields exist and you put waves in it. Okay, so there's a thing, a junk that's here, and the junk ends up being waved. It's not like you're creating a wave of soldiers. It's like the soldiers already exist, and then you put them in arrange them in a order, by pushing on them. But they're already there, and they're always there. And that's the big difference between a theory that says the field is made up of energy that's always there, or whether it's made up and the energy just has to do with whether the soldier is, I don't know how to even, whether he's holding his arms out or holding his arms in, or whatever the, pushing forward or not pushing forward. I mean, it just has to do with reshaping the stuff that exists in a pre-existing medium versus actually having bits in the medium, actually forcing there to be stuff. Like the corn has to actually grow. Well, let's say the corn is a good example for their ether, because they're just talking like it's being blown in the wind. And the argument to be made is that no, the stuff has to actually be like tumbleweeds. It has to be blown onto the surface. The tumbleweeds they have to come from somewhere, and they're going somewhere. And the field is a desert. There is no field.
And that was kind of, at the time of Maxwell and people like that was kind of the way people thought things worked. So another important development in the 1800s were, physics really started galloping along. After Galileo and Newton, physics kind of got in gear.
So that's kind of a funny thing to say, right? I mean, that's the deadest years, from Newton to 1900s. Those are the dead years. They spent 150, 200 years just walking around in circles. They drew no conclusions. They added no value. It's like they didn't get anywhere at all.
It started to happen. There's a lot of different kinds of phenomena in the world. Another important area is heat. The theory of...
Well, that would be the only place where they gained any knowledge in the steam engine kind of thing. So they did do something about but see, again, that was all just Edison type invention. That was just all utility. It wasn't theoretical. There wasn't any great theoretical knowledge gained. There was just a bunch of in terms of understanding the nature of an atom. There was just some, how can we put this to use? Heat creates pressure. Pressure can be controlled, valved, and therefore we can make it move in the directions we wish it to.
The idea of temperature, the theory of heat, those kinds of things. There's a big debate in the 1800s. What is heat? So it got a little bit weird and funky. I mean, it was already suspected in the 1600s that heat was somehow associated with the microscopic motion of the things that made up matter. And even, for example, one of the Bernoullis had figured out that gases might be little molecules all bouncing around. That was in the mid-1700s. But that nobody really particularly cared about that. People were very much concerned about heat, and then when steam engines were invented.
Right. So the idea is that you're taking something that's going in all directions and you're containing it in a box, and so it's pushing in all directions. And the fact is you can open any one of the directions. So sort of like a wheel spinning, I can put a surface against it in any location and pull energy in that direction. So if I want energy in this direction, I just put a surface onto a spinning wheel in that direction, and I can pull the energy off in that direction. Well, the same is true with pressure in a box. I can just put pressure in a box, And I can put a hole in the box in any direction, and I can create force in one direction, which has use. Force in every direction doesn't have any use, but force in one direction, I can make that do something. I can make that do work.
It was important to understand kind of what was possible in steam engines. Sadi Carnot worked out the notion of an idealized steam engine and tried to work out how much energy you could get from an idealized steam engine, these kinds of things. But this notion of what is heat?
Idealized is a dangerous word, right? Because then you're arguing, what, can we have an infinite amount of pressure? Because your containers can't hold the infinite amount of pressure. There's no container for it.
What is the thing that corresponds to heat? Wasn't clear. And it got kind of weird, and a little bit like the ether. There was this notion of things like phlogiston, this substance that would suffuse things and that corresponded to heat. This idea that it was that heat wasn't a substance, that was a property. It was just a property of things, not its own separate
Yes. See, it is just a property of something. And it's just the property is if the atoms are moving, they're being pushed. So there has to be force in there. There has to be the stuff that has momentum. There's stuff that's got legs and can walk. That's the force. And then there's stuff that doesn't have any legs. And if it's moving, it has to be pushed by people that have legs. So it's like people versus rocks is what the universe is made out of. And if you just understand that the people are always walking. They never stop walking. And when they hit a rock, they push the rock, but they don't get as far walking. Their walking step is cut in half. And then you can understand that, oh yeah, I can get it. That a bunch of people come walking into a circle, all right? And while they're in the circle, though, they're pushing rocks, and so they don't come out, okay, when they should have. So there's a lack of energy. They've consumed some energy by wasting their walking speed. All right, so they went in walking big steps. While they're inside, they're walking little steps. So now the external universe has a lack of walking happening in it because the walking steps got smaller while they're in there pushing the rocks. I mean, there's lots of analogies. I'm just adding value to what he's saying in the sense that there's a grain of truth. But if you focus the camera, you can see what it is. You can see the difference between a seed and a rock.
A separated kind of substance. That took until the mid 1800s before that started to become clear, and there started to be experiments. People like Joule, who did experiments sort of about the interconvertibility of heat and other forms of and energy, and things that were known from mechanics, things about the energy of motion that was understood from mechanics. And by the way, following Newton and so on, the idea of the conservation of momentum, the conservation of mechanical energy, these were things that had emerged from mechanics, but it wasn't clear sort of how heat fitted into that.
It was clear that, the word conservation really just means that there's a part of this that you can't kill. That the little walking people are eternal, and they're always walking. And all you can do is slow them down for a period of time when they're actually moving a rock. But other than that, they're always moving through system to system. You can have them jump from one system to another system or walk to another system. But it's always somewhere. So if there's rocks moving over here, okay, you can know that there's energy doing something. Then it's not free in the universe, and that means that the universe has a little less pressure in it because some of the walkers are walking slower. But the idea is that never stops. The energy is perpetual and inevitable and forever, and it doesn't stop. You can just follow where the energy goes, and there's never any place where it just disappears. There's only a place where you slow it down, where you retard its progress, which is a kind of destruction of its momentum, but you have something for that. You have the fact that you move the rock from here to here. So the difference is that the energy is conserved in the sense that it's in the movement of the rock.
Well, then 1850-ish, sort of big point, the first law of thermodynamics, the idea that heat is a form of energy, and that the energy of mechanical work, like kinetic energy, is sort of interchangeable with the energy of heat. And so
when he says this, the heat is a form of energy, there is only one form of energy. It's in the form of the little bits moving the speed of light. So the little bits of momentum, whether it's a photon or being displayed by magnetism or electricity or gravity, no matter where it's being displayed, okay, it's always the same thing. It's just something moving the speed of light. That's all there is. There's a bit moving the speed of light, and there's rocks. And that's all there is.
That was kind of a thing of around 1850. People like Clausius, I think, was involved in that. This notion of heat as a...
And just let me say, the rock, you can't make the rock roll down a hill somewhere. If the rock is moving, there has to be a sycophist. There has to be a little energy thing that's occupied pushing it. So the rock only moves while there's something with legs pushing it. And as soon as the thing with legs stops pushing it, it doesn't move anymore. So there's no perpetual energy for rocks. If you see a rock moving, the rock is moving because there's force being used to move it.
Of energy, interconvertible with mechanical energy. Well, the only thing was that it was clear it wasn't completely interconvertible, because if you had something that was hot, you couldn't immediately turn that thing that was hot, into useful mechanical work. And so it was kind of like, why is that? What's going on there? And that's what became the second law of...
See, but you can, so that, I don't even know why you said that, but that's what they're discovering. You're discovering it. I mean, they already knew they could convert it into work. They knew they could start a fire below something, and there would be energy pressure from the fire, and they could make a piece of paper float. I mean, they could get action out of the energy. They could transfer it. It's just that they didn't have any really great ways to do that, okay? They didn't have some great conversion mechanism. And then they invented the steam engine, and they created a pretty substantial and great conversion mechanism.
Thermodynamics, what we now often refer to as the law of entropy increase. But back in those days, it was kind of this law that said you can't get mechanical work out of heat energy that easily. And so, for example, a common version of it would be the statement that heat doesn't spontaneously flow from a colder body to a hotter body.
It's sort of, look, the difference between a light bulb and a laser. Okay, so you could argue that for the people in the 1800s, it was like all they had were light bulbs, so they didn't have great ways to confine the energy in one direction. It came out in all directions, so you had to light things you didn't want to light. I mean, you could put a reflector behind the light, you can get some enhancements, but then you're heating up the metal and blah, 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 and you're doing all kinds of other stuff that you don't want to do. So there wasn't some great efficient way, but it wasn't like it was theoretically impossible. It was just that it was not mechanically possible at the time.
That was one version of the second law of thermodynamics. But it became slowly clearer what the second law might be, and this notion that, and we now know that the issue is mechanical work involves, you take this big lump of stuff and you start it in motion. And that means all the atoms in that big lump of stuff are all going in one particular direction. If you just make the lump of stuff hot, it means the atoms are moving around. They're moving around very quickly, but they're moving around in random ways. And we can't kind of decode that randomness so that we can kind of organize it into this sort of systematic mechanical motion.
But again, that's what all of the Industrial Revolution is sort of made out, is making those light reflectors, making the ways of making it more efficient and more one-directional, making the nozzles on a rocket ship. Figuring out ways to take an explosion in all directions and convert it into motion in one direction. And so, yes, all of that was being figured out.
That failure to be able to organize it is, I think, the origin of the second law, but we'll come to that.
I mean, you almost say the electric motor is taking advantage of this, this idea that the energy is in all directions, the spin, the circular motion, but you convert it into motion in one direction.
But anyway, back in those days, this notion of the second law sort of emerged 1860s-ish, kind of starting to be really talked about. Two big things happened. So James Clerk Maxwell, actually before he worked on electromagnetism, worked on kinetic theory. He worked on a prize essay about the moons of Saturn, and in it he invented what is now called kinetic theory. He invented kind of the mathematical theory that describes, you have a bunch of gas molecules bouncing around. What can you say about the properties of those molecules? So one big thing he said was,
I think it was the rings of Saturn, actually. So it's the moons of Saturn. It's one, they are moons, I suppose, but moons in little tiny pieces. So it was the rings of Saturn, that, particulate theory.
The distribution of velocities of those molecules is this Gaussian-like distribution, e to the minus mv squared distribution that is now called the Maxwell-Boltzmann distribution. So that was a sort of a mathematics meets the kind of the mathematics meets the idea that gases are really a bunch of little particle-like things bouncing around. That was a Maxwell idea. Then along came Ludwig Boltzmann, and by 1870 he had proved this thing called the H theorem. So there'd been this idea in trying to characterize what heat was relative to other forms of energy. There'd been this idea, I think, due to Clausius, that you could define a notion of what's called entropy, which he defined as a thing that was essentially heat divided by temperature. So what Boltzmann proved?
Yeah, so kind of a nonsensical thing, right? I mean, just heat divided by temperature. What? That doesn't make any sense.
Was on the basis of...
I mean, it's temperature divided by temperature. What the fuck is heat except a temperature?
Molecules bouncing around. He proved this thing called the H theorem that he said meant that he proved that the entropy, as defined by Clausius, always increases. And that's equivalent to statements like heat doesn't spontaneously flow from a colder body to a hotter body. It's equivalent to a lot of other kinds of statements. And so Boltzmann said he proved that. Now,
yeah, it didn't prove anything. Obviously, it all depends on the size of the thing you're moving and the form of the heat's inside the heat is inside the heat, right? The atom itself has got a temperature. The electrons and protons are vibrating, a certain amount. Then the atom itself is moving, right? And then the clumps of atoms, the compounds, are turning and moving. If they're turning or twisting or spinning or doing different things, that's all a form of these force that has to be constantly being used to do all of that motion. So all of the motion combines. And so that's where it just gets really complicated, is because the heat isn't just in one place. The heat is inside the atom. The nuclear bomb kind of shows you there's heat in there. There's people with legs.
His proof was kind of a bit of a sham. It's an interesting mathematical proof, but because it turns out the laws of physics are reversible, at least in the sense that they, whatever the laws of mechanics have the property that if you can have two things that collide like this and go out like that, you could sort of run the movie in reverse, and they could come in from where they started, from where they ended up, and go back and get back to where you started from. And so that reversibility was kind of, Boltzmann had gone from...
So this is a part of physics, like who cares one way or the other, but this is just the cause and effect part. So it's sort of important in the sense that nothing really challenges that fact, that it's all reversible. The problem is that we can't reverse things in the right sequence. So when something happens, there's some things we can't reconstruct the reversal, in the sense that we can't control the sequence of events that took place, because they have to happen in exactly the right reverse order. So, it's just about the fact that there's too many atoms and too many bits and too many electrons and too many protons that we can't control the reversal. We don't have any mechanism that can push back or go backwards or create the reverse motion that controls enough of those atoms to initiate that reversal. We don't do it in the right sequence. We don't hit the right atoms at the right time. And so it's out of sequence, and therefore as soon as you break the sequence, just a couple of atoms are off, the whole thing is broken. So you can't go backwards. It's like going backwards with your genealogy. And if you said, okay, I'm going to push it back, but you got a couple of the interactions, the marriages in the wrong order, the whole thing's not going to work. You're not going to get back to where you were originally. You're going to get back to something completely different, because it's all dependent on precise order of what electron hit what thing when. And we just don't have a container that can reliably reconstruct, stop it as exactly as it is and then reverse it. There's no mechanism we can do that with. We can't push back exactly in the order the last step. We can't go to the step just previous to this one and the step just previous. We can only push back in some sloppy way. And as soon as there's a bit of sloppy, that little piece of error will get bigger and bigger and bigger.
That mechanics that was reversible.
One error in this, you could almost argue like in a race, a running race. One error at the start, just gets compounded through the race. It's critical, the start.
And it proved that something irreversible happened. It was the so-called reversibility objection. And that was a very obscure thing. In fact, it's one of my sort of favorite physics misguidedness things is that in textbooks, modern textbooks, they'll often talk about the second law of thermodynamics. They'll show Boltzmann's proof of the H theorem. They'll say, well, yes, you can run everything backwards, and how can it not? How can you then conclude that entropy increases rather than decreases? They'll often end with statements like the last sentence being, this point is often puzzling to the student. Well, actually, it's been puzzling to everybody else too. I think I finally figured out in the 1990s, actually, how this works. And really the story is, the story is that what's happening is everything is reversible, but the dynamics of the system is effectively doing encryption on the initial conditions of the system.
No, it's not encryption. It's just, look, the systems are always more complicated than we can control all the parts, and so therefore we just can't push it back in the right order. We mess up the start, and that messes up the ending.
So while in principle you could reverse it, you need to be a cryptanalyst to do it, so to speak. And in practice, when we do experiments or make observations, we're not as computationally sophisticated as we would need to be to do that reversal. So even though looked at a microscopic level, everything is perfectly reversible, it doesn't appear that way to an actual observer. That was a kind of an idea that Josiah Willard Gibbs, one of the...
I just think it's a solid, theoretical point to make. Now, whether you can find evidence to prove it one way or the other, I'm just saying that I think obviously cause and effect is real. And so, yes, it's completely reversible.
Early American physicists from the early 1900s, he was big on this notion of coarse graining in statistical mechanics, which is kind of his version of saying the observer can't figure out at the level sort of molecule by molecule what's going on.
Exactly. So there's no point. There's no point in talking about ever reversing anything, because we can't make a system where we can control the granularity.
This computation idea, but he just had the idea of you can't look at the individual molecules and see what's happening.
I mean, they can do it in systems where you control that, right? So when you take out a lot of these irregularities of the pushback, they can put a drop of ink in some medium and then swirl it, 100 times, and then it blends in and changes the color of the stuff, and then they just unswirl it. They just spin it backwards, and the little drop of ink goes back to a drop of ink. So clearly we have clear indication that that's the mechanism. The mechanism is that it is all reversible. It's just that you need to have a very controlled environment, where things are moving in very consistent ways and in few ways. The more scattered you have and the more deflections in bizarre ways, then the less chance you're going to be able to see it, because we're not going to be able to create a system that can reverse it in the same way that it was created.
I mean, Maxwell already had this thing called Maxwell's demon, where you've had a thought experiment where he said, imagine there are these two sides of a box, and there's a trapdoor in between them, and there's this little very tiny creature who is watching when molecules arrive at that trapdoor and is deciding whether to send them to the left or to the right. And with that demon, you can always get a violation of the second law of thermodynamics. By having sort of intelligence like that in the loop, you can get this violation of the second law. And that's kind of like saying, that's a kind of the beginnings of saying you sort of need a cryptanalyst to figure out how to untangle the inexorable.
But see, the irony here is that this is Maxwell, this is magnetism. That's exactly what a magnet's doing. It's a filter. So it's taking something that comes in, and it's saying, well, if you're blue, you go this way, and if you're red, you go that way. And it's doing that little demon thing. It's creating a mechanism, a little physical mechanism that's actually doing a left-right.
Increase of entropy associated with the second law. Actually, I should mention that one feature of the second law was that, particularly late 1800s, it was this whole question of, was there a life force? Was there something about living systems, about biology, that was fundamentally different from physical systems? And it had been a long-standing question of, is there some spark of life that is going beyond the physics, the chemistry?
Oh, crap. I didn't hear this part, I guess. I just didn't pay any attention, I suppose. No point in bringing this crap in here. Religion.
So on. And that was what... So the second law was often kind of invoked in a, well, most things show the law of entropy increase, but living systems can sort of do the opposite. Well, they can't really. They can only do it temporarily, and they can only do it in a sort of a Maxwell's demonish kind of way at the level of individual molecules, but it doesn't really last. But in any case, that didn't become clear until well into the 1900s. And what really happened is this notion of what were the foundations of the second law, which I think is a fascinating thing. It's one of the things that got me interested in physics back when I was about 12 years old or something in 1972, was understanding things about the second law of thermodynamics.
72, 12, so we're about the same age, right? No, he's 10 years younger than me. What? He was 12 in 72. Yeah, we're the same age. Yeah, I was 12 in 72. Yeah. Yeah, so we're the same age. Funny.
And it's sort of shocking that so little work has been done on it. And when I finally figured out how it actually works, I don't think anybody cares. But I think it's really interesting.
Yeah, well, I can't say I was thinking about thermodynamics when I was 12, but I did think about photons and didn't like what I was hearing at all.
Back to I should mention, by the way, I mean, by the time after the whole life force thing sort of dissipated, by probably the 1930s, people had the point of view that the second law was just true. It was a fundamental true fact about nature. We sort of maybe kind of didn't maybe even need to prove it, or maybe Boltzmann had proved it, or people were kind of confused about it.
Well, we already know that energy moves through systems, so it just makes sense that, well, you just make it move the opposite direction, and it's all a bunch of straight lines. The whole thing comes down to straight lines. Everything's moving because the force moves in straight lines. People walk in straight lines. So the force, you have to understand, doesn't have any knowledge of bending or curving or any of that crap. It just says, I'm a goer this way, I a goer this way, until I encounter something that forces me to go some other way. And the force would be, I'm pushing a rock, and then somebody else starts pushing my rock this way, and then all of a sudden now I'm going this way because somebody changed the way my rock is moving. That kind of thing. That there's no I'm going to curve for the fun of it in real space. And once you know it's all straight lines, then you can reverse straight lines.
I mean, the idea of entropy got kind of a boost in the 1940s when Claude Shannon introduced the idea of information
Oh, silly. The idea of information was that's where they really went sideways, when they start calling it information. Clearly, it's informative to know that there's a bunch of soldiers coming for your house. It's informative. It's information. Oh, yeah, there's a bunch of soldiers coming. But it's not in any way, does it mean anything? Doesn't change the fact it's a bunch of soldiers. I mean, calling them information is okay, but it might be better to call them Nazis or something else.
Of sort of the compressibility of data, because basically his information measure is exactly minus the Boltzmann's entropy measure. Okay, so another big thing from the 1600s, from the 1800s,
yeah, well, he's been doing this for an hour. It's 2 hours and 2.5 hours of just babbling. It's pretty good. I have to give him credit.
The whole notion of atoms really becoming real. And it had been known, chemistry had developed a lot. Lots of chemical elements were known. By the 1860s, Mendeleev was sort of writing his chemistry textbook and making up a periodic table, all those kinds of things. This notion that there was a systematization of chemistry was becoming clear. Meanwhile, people like Dalton, even at the beginning of the 1800s, had noticed things about chemical reactions. They'd noticed that when you wrote down chemical reactions, things worked very nicely when there were sort of integer multiples of things that showed up all over the place. It was like there were 2 units of oxygen and 1 unit of hydrogen, or whatever it is, for different kinds of things. And that sort of it was very convenient if you could just sort of numerologically arrange things by saying there's a discrete amount of hydrogen, and there's twice as much hydrogen as there is oxygen in water in some sense.
Yeah, so they was sort of getting to all this idea that it's all made out of one thing, like this hydrogen atom is, then you got 2 hydrogen atoms and 3 hydrogen atoms and 4 hydrogen atoms, and you're really just making a bigger atom out of smaller atoms, and all of those kind of notions. So obviously it would break down in the sense that once you could rip off a hydrogen worth, or that kind of thing. You could break things the same way you could make things. It's probably a good way to say it.
And that there were these sort of simple.
You always had to have this to keep any balance. You always had to have a piece of the negative and a piece of the positive.
And so he kind of developed this idea that there must be an atomic theory that would underlie chemistry, but it was done more at the level of sort of explaining chemical reactions. Meanwhile, it's sort of been known for a while, but it kind of was really became clearer with a guy called Robert Brown, discovered Brownian motion. It had been known for a long time that things like this happen. That if you have a light enough thing, he was looking at pollen grains, it would be sort of discretely kicked around if you were looking at it under a microscope. And that discrete kicking around, people sort of started identifying, oh yeah, that's actual molecules that are like doing the kicking discretely. And so there's
right. So the interesting thing would be is how much of that do you have in space, So, but we know the atmosphere is hot, so we know that the atmosphere is going to cause things to move around just because the atmosphere is moving around. The bits inside of it are smashing into each other, they're sending smashing messages. They're sending soldiers to each other's houses and pushing them about. And each one is being pushed by a different number of soldiers, and so they have all different velocities. And each time there's an interaction, there's 5 soldiers can leave, or 2 soldiers can leave this way, and blah 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 blah.
That atoms, that things are made of discrete stuff, was pretty much established. And by the time Maxwell was talking about kinetic theory, it was like, yeah, things are made of discrete stuff, discrete atom-like things. What were atoms? People didn't know. Actually, one of my favorite kind of theories, due to William Thomson, later Lord Kelvin, was the idea that atoms were knots in the ether. So remember this ether, the luminiferous ether that was supposed to...
Yes, we can imagine lots of stuff, say lots of stuff, but the point is you have to make a more complete proof. And so I can argue, okay, that the irony is that the matter is the dead stuff. It doesn't do anything until the force tells it what to do, until it's being pushed somewhere. So the rocks are just being pushed around. The rocks don't have anything else they're doing. They're just dead rocks. And it just has to do with what can push on them. And so you could argue that little red soldiers can have hands that can push on them, and blue soldiers can't push. And blue soldiers get changed in their direction.
Fill the universe and be the thing that was the sort of carrier of light, as air is the carrier of sound waves. Well, so the idea was that knots, there are discrete kinds of knots that you can tie in pieces of string. There are different kinds. You can classify the knots that exist. And Kelvin's idea was, well, gosh, it may be that we know there are discrete kinds of atoms. Maybe the kinds of atoms all correspond to knots in the ether. A completely non-stupid theory. It turns out to be basically wrong, at least at that level.
Yes, right. So they're all non-stupid theories, right? So the guy Faraday, had a gear theory. Gears inside of substances, and it's not a bad theory for the time, but it's wrong. It's just not right.
Definitely not a foolish thing to think about. And in fact, a lot of knot theory was produced by a...
But see, the difference is right in his description of his theory, Faraday says it's just what I'm thinking, and it doesn't really work, and it's not complete, and don't take it too seriously. I'm not proposing it as an idea. And that's what these physicists aren't doing, is saying that, it's just not good enough. So I'm sure Newton had thoughts about gravity in different ways that it could have been produced. But he says, I don't have anything I can hand you as an answer because it's just not good enough. And physics stopped saying it's not good enough. In the 1930s. That's when they just said, no, we want to have answers. We don't want to do this. It's not good enough stuff anymore. We don't want to admit the truth that we don't have enough evidence.
A childhood friend of the Maxwell's, a person called Tate, who started classifying knots to try and see, would there be 92 of them, just like there were chemical elements, and that number of chemical elements and so on. Okay, so anyway, so this takes us let's see, I think I'm looking at questions from the live stream here. This kind of takes us to pretty much the end of the 1800s in terms of what was happening. So a couple of things happened right at the tail end of the 1800s. First, 1895, discovery of X-rays by Röntgen, discovery that you could have these things that would kind of go through matter and would make nice pictures of bones and would not go through bones but would go through other pieces of us, so to speak. Then very soon thereafter, Becquerel discovered natural radioactivity, and then 1897, Thomson discovered the electron.
So radioactivity is kind of complex because it's not. It's alpha, beta, and gamma, and then you don't even know whether those are complete descriptions in the sense that all you're doing is a simplistic division, based on a magnetic field, and ions will, behave like negative things in certain circumstances. Although they're a dipole, depending on which way they're pointing in any one point, they're a dipole from this direction, but they're a monopole. If you take a magnet and show it to you this way, the lengthwise, well then it's a dipole. If I show it to you this way, it's a monopole. So ions get a little more complicated, and they're part of the mix. So the radioactive substance isn't just producing light. of invisible frequencies and some visible ones depending on the radiation. It's also producing chunks, pieces, bigger pieces.
Electricity was also made of discrete stuff, just like matter was made of discrete atoms. So electricity was made of discrete things, namely electrons. Well, okay, so there have been a bunch of things that have been studied. One thing that had emerged in the I think 1880s or so was this notion of black body radiation. So the question was, when you heat something up, it glows. We know that. What color does it glow? What is the distribution of colors? What is the distribution of colors of electromagnetic? So we know that light is a form of electromagnetic.
So this was, in my opinion, kind of a wrong-headed way of looking at it, because you're just measuring frequencies. And so they had this idea that there's some sort of, you could have an infinite frequency. That is, you could just keep making the distance between the pieces of momentum, if you think of them that way. There was some scale that just went forever. And instead, no, there is a finite, what you can get out of atoms kind of thing. There is discrete distances between things, and you can't get any smaller than the Planck length or something. So you can go so close and no closer, kind of argument. Once you get rid of all the space between things, there's no more space, and it's just a fact. You can mathematically do this half the distance thing, but you can't do it in the real world. In the real world, there's no half the distance. You actually do cross the finish line.
And so when something is heated up and glows, what colors does it produce as a function of temperature? So there was a way of calculating that based on kind of standard, based on the fact that there might be little generators, little oscillators that would be like little radio transmitters, except for light in the material, and there might be lots of these, and they might all produce a certain spectrum of electromagnetic radiation. Problem was that calculation gave completely the wrong answer. And by 1900, there were pretty precise measurements of what the actual black body spectrum was. And so a chap called Max Planck decided he would fit that data. And he realized that you could get a really good fit to that data if you assume that somehow that whatever it was that were these little oscillators that were producing electromagnetic radiation was somehow quantized, were in lumps. A little bit like, and he got it wasn't Maxwell's distribution from kinetic theory, the distribution of speeds of molecules, but it was something a little like that, a little bit different from that. What we now call the Bose-Einstein distribution, that would govern if sort of electromagnetic radiation was quantized, that would be the form of black body of the spectrum.
So anyway, this is a little more complicated than I think you can. Maybe you should just took more time on one subject, but it's just this curve you get, and then it falls off at the end, and the falling off just means that it's harder and harder to make photons that have higher and higher energy. Because to make them, you have to create pressure. All right, so it's the ping pong paddle argument, right? To move the paddles closer and closer, to overcome the amount of hitting that the ball trapped between them is doing, right? I have to apply more pressure, so I have to have more energy to create that more energy. And there's no circumstance inside the atom that allows you to make that much pressure. So there's only a limited amount of pressure you can possibly have in one quanta.
Body radiation. So that was kind of the first idea of quantization of something, in this case, quantization of light, effectively. So it was already known there were discrete atoms, there were discrete electrons for electricity, but what about light? Well, Planck sort of had this empirical fit that said there could also be discreteness in light. Okay, there was a thing called the photoelectric effect. You shine light on something, on some materials, and they emit electrons, basically. They produce, the photoelectric effect is what's used for photocells, it's what's used ultimately for the I guess it's what's used for the imaging device that is the camera that I'm waving my arms at you guys using. Is that?
Well, technically it couldn't be, right? Because you have red in you and you have all these colors that aren't supposed to be able to produce the effect. But so the photoelectric effect is a specific launching of electrons. You're not causing the launching of electrons, you're causing the photoelectric effect in the sense that there's a photoelectric effect that also produces electricity. So the one that produces electricity doesn't require you to have high energy photons. It just requires any energy photons to create the electrical effect. The effect of shooting an electron off the material, well, that's a different effect. So that's where it sort of gets, confusing in the sense that the photosynthesis idea is combined with the photoelectric effect idea when they're two mechanically different things. Electricity is different than just ejecting electrons. Electricity is something specific to what atoms are doing.
Same photoelectric effect. But in any case, the photoelectric effect, there were things known about the photoelectric effect, about what frequencies of light would produce electrons, etc., etc., etc. 1905, Albert Einstein figured out that if you believed Planck's idea of discreteness of electromagnetism, if you had the notion of a photon, a discrete particle of light, you could explain the photoelectric effect.
But see, the problem is that I go back to this, is that although I agree, okay, that it's quantized in the sense that the force is always in clumps, okay, the momentum is in little pieces of momentum, and you can have the pieces of momentum at a frequency, and so that works, and that's right. But the deduction they drew from the way we saw light, the only way we saw it was because it made electrons move. So clearly electrons can only move as single electrons. So you're clumping the photon by having the minimum of moving a clump. So you're looking at photons with a clump detector. So obviously you're going to see the photons as clumps because you're using a clump detector to detect them. The detector has already dictated that you're not going to see the energy in any other form than one that has the minimum amount of energy to move the electron. So if it doesn't move the electron, you're saying it doesn't exist. And so that's like saying it doesn't matter how many snowballs you throw at a big snowball and you're going to roll it down a hill. Well, you know that it just kind of depends on what you throw and how you throw it. But the big snowball moving doesn't tell you that it comes in clumps.
It's actually what Einstein eventually won his Nobel Prize for, because relativity was way too controversial still, was the explanation of the photoelectric effect. So also, another thing that was happening right at the end of the 1900s was a thing called the Michelson-Morley.
Well, relativity was silly. It was silly, it is silly, it always will be silly. It's going to be on the ash heap of silly. That's where it's going to be eventually. Eventually, there a whole, you're all going to have to admit, oh shit, my father was full of shit, and that old Wolfram guy, oh blah blah blah, yeah, he was full of shit, and thinking that crap had any valuability. I mean, it's just a silly theory. Space, time is silly. Bent space is silly. Time is a function. It's not a place.
Experiment. Michelson-Morley experiment was an attempt to detect what was called the ether drift. So assume that the universe is full of luminiferous ether.
Which is the basis of your entire field theory, is that the field already exists, and all you're doing is telling one soldier to poke the soldier in front of him. You're not putting real soldiers in the field doing real work. You're putting a bunch of vibrations or movement in a bunch of dominoes. Well, you don't need the dominoes. You can just flick the domino from here to there. I don't need to hit a bunch of dominoes to get the domino to go from here to there.
The Earth must be moving through the luminous ether at some speed. But that means that somehow, just like sound waves, if you're moving through the air, sound waves work differently than if you're stationary in the air. And it should have been possible to detect that change in the luminiferous ether as a result of...
So the drag, we're back to the drag subject, and the irony is, again, that the elemental bits appear to be dragged to a halt. The elemental bits, the electrons and the protons, do run out of gas. They do. They don't. You can't just throw one in space and it just keeps going happily on its way. They go a certain distance and that's it. They run out of energy.
Around the sun at different times of year and so on, you should see different features of the transmission of light. Well, they didn't see that. And so that meant there was no ether drift. This idea that there was this ether that sort of filled the universe and that was the carrier.
So there's no point in even going into the Michelson-Morley thing, right? The interferometer, something they fundamentally don't understand because they fundamentally don't even see the obvious, that there can't be two equal beams that come out of the beam splitter because the beam splitter is doing something completely different to the two beams. One is spreading through the whole experiment, the other one is not, diverging, getting bigger and bigger as a beam. I mean, fundamental differences, and they don't even concede these obvious and fundamental differences, that obviously the path length of the light is different, merely because it's on a different vector. So anyway, it's probably enough. Might do more of this sometime. I mean, I haven't watched it all the way through yet. I haven't gotten to where he gets into all the modern crap. I mean, he gets into the particle zoo, and I don't know if he's going to even talk about it. He has an alternative theory, some sort of unification theory that somehow unifies all this mush. But again, it's really just a computer program, so it's not really a theory in my opinion. But we'll see. It has some particle element to it of some kind, but what I've seen of it is incomprehensible so far. I can't make any real sense out of it. It's all a bunch of, looks like string theory, a bunch of wooey, la la la, a bunch of garbage in and a pretense of order out, based on 5 million assumptions. And no simple mechanism underlying anything. But anyway, we'll get to that. So, enough of a video and such. I feel like it's enough. Yeah. So, interested in, again, counter arguments. Somebody can make somebody wishes to defend the volume of evidence proving any of these fundamental notions of bent space and entanglement and superposition and all the spooky action crap. Want to defend any of this and in some way point out how anything I've talked about is this simple thing, force, matter, and interaction, that everything does have to be forced to move, everything that we call a thing, matter, and that force is a piece of its momentum is occupied through that process of moving matter, and that's what creates gravity. So it all fits. And I'm not hearing any rational counter arguments, and so we're just waiting for the right answer to rise to the top, and it's never going to get there if nobody says, hey, that sounds like a better answer. And if everybody's afraid to do that, or what's the where is my argument, my appeal to this jury, pointing to the evidence, showing how their evidence is completely flawed, showing how their foundational, their cornerstone experiment, the two-slit experiment, is completely based on nonsense assumptions. And it can be explained as simple scatter. Demonstrating that their theory is all wrong-headed. Wrong direction, wrong road, wrong path. The right road is right over there. It's paved. It's got white lines on it and all kinds of stuff. It's all finished and done. It works. And you're sitting here going across this bouncy, mud-covered, sloppy road, and I'm explaining, why are you doing that? Why are you defending this rocky, crappy road when there's this beautiful, paved, perfect road right over here that makes perfect sense, is simple, does all the things that physics should do? It's physical, no magic, no woo. Come on. No crooked lines for no reason. Anyway. But nobody can make any kind of counter-argument videos. Nobody can do anything. There's no way to have any interaction on this medium. It's just amazing. I mean, a civil one. Reasonably civil.